Nenomatica, where mathematics meets YouTube excellence. Welcome to our mathematics video. Today, we'll be exploring the third law of radicals, an important property when working with roots and exponents. The third law of radicals deals with taking numbers in and out of radicals. Let's look at the formal statement of this law. Now, let's go through the proof of this law step by step. We start with the left side of our equation, a times the nth root of b. First, we can rewrite b to the power of 1 over n as an alternate form of the nth root of b. Next, we can apply the law of exponents to rewrite a as a to the power of n over n. Now, we can use the power property to combine these expressions. This gives us a to the power of n times b, all to the power of 1 over n. Finally, we can convert this back to radical form, giving us the nth root of a to the power of n times b. Thus, we've proven that a times the nth root of b equals the nth root of a to the power of n times b. It's important to note that this law also applies when n is odd. For any real numbers a and b, when n is odd, let's consider a special case. If n is even and is a negative number, and we want to bring inside the radical, we need to place a negative sign in front of the radical. Let's work through a simple example to better understand this law. Example, simplify the expression 2 times the square root of 9. Using the third law of radicals, we can rewrite this as the square root of 2 squared times 9, which equals the square root of 4 times 9, which equals the square root of 36, which equals 6. Let's try a more complex example. Example, simplify the expression 3 times the cube root of 8. Using the third law of radicals, we can rewrite this as the cube root of 3 cubed times 8, which equals the cube root of 27 times 8, which equals the cube root of 216, which equals 6. Let's examine the special case where n is even and a is negative. Example, simplify negative 3 times the square root of 4. Since n equals 2 even and a equals negative 3 negative, we need to be careful. Using the special case formula, negative 3 times the square root of 4 equals negative times the square root of 9 times 4, which equals negative times the square root of 36, which equals negative 6. Let's summarize what we've learned about the third law of radicals. The third law of radicals states that a times the nth root of b equals the nth root of a to the power of n times b. For even values of n, both a and b must be non-negative. For odd values of n, a and b can be any real numbers. If n is even and a is negative, we need to place a negative sign in front of the radical when bringing it inside. This law is very useful for simplifying radical expressions and is an important tool in algebra. We need to verify the equality. The square root of 2 times the fourth root of 8 equals the cube root of 32. To verify this equation, we'll use a key property of radicals. The rule says that a times the nth root of b equals the nth root of a to the n times b. We'll start by applying the radical multiplication property. Using the formula times the nth root of b equals the nth root of a to the n times b, we can rewrite this as the fourth root of the quantity square root of 2 to the fourth power times 8. Next, we need to simplify the expression under the radical. First, we calculate square root of 2 to the fourth power. When we have the square root of a number raised to a power, we can simplify by multiplying the exponents. So the square root of 2 to the fourth power equals 2 squared, which equals 4. Now, we multiply 4 times 8 to get 32. So our expression simplifies to the fourth root of 32. And that's exactly what the right-hand side of our original equation was. So we verified that the square root of 2 times the fourth root of 8 is indeed equal to the fourth root of 32. Now, let's move on to our second example. We need to verify that negative 2 times the square root of 3 equals negative square root of 12. Again, we'll use the radical multiplication property to verify this equality. We'll apply the same rule. A times the nth root of b equals the nth root of a to the n times b. Let's begin with the left-hand side of the equation. Negative 2 times the square root of 3. According to our property, we can rewrite this as negative 1 times the square root of 2 squared times 3. Now we simplify under the radical. 2 squared is 4, and 4 times 3 equals 12. So our expression becomes negative square root of 12. And that's exactly what the right-hand side of our original equation was. So we verified that negative 2 times the square root of 3 equals negative square root of 12. We want to simplify the expression. 2 root 2, where the 2 outside is a coefficient and the 2 inside is under a square root. We'll use our property which states that a times the bth root of b equals the bth root of a to the b power times b. So we rewrite this as the fifth root of 2 to the power of 5 times 2. Let's compute. 2 to the power of 5 is 32, so we have the fifth root of 32 times 2. This simplifies to the fifth root of 64, which is our answer for the first example. Now, let's move to our second example. This time, we want to simplify the expression. 2 times the cube root of 3. We'll use the same property as before. So we rewrite this as the cube root of 2 to the power of 3 times 3. Let's compute. 2 to the power of 3 is 8. So we have the cube root of 8 times 3. This simplifies to the cube root of 24, which is our final answer for the second example. We need to simplify the expression 3 times the fourth root of 3. According to our rule, we can rewrite this as the fourth root of 3 to the fourth power times 3. 3 to the fourth power is 81. So we get the fourth root of 81 times 3, which equals the fourth root of 243. Let's move to our second example. We need to simplify the expression negative 5 times the square root of 2. Using our rule, this equals negative times the square root of 5 squared times 2. 5 squared is 25. So we have negative times the square root of 25 times 2. 25 times 2 is 50. So our expression becomes negative times the square root of 50. Therefore, the simplified form is negative square root of 50. Let's look at our third example. We need to simplify negative 2 times the cube root of 3. Applying our rule, this equals negative times the cube root of 2 cubed times 3. 2 cubed is 8. So our expression becomes negative times the cube root of 8 times 3. 8 times 3 is 24. So we have negative times the cube root of 24. Therefore, the simplified form is negative cube root of 24. For our final example, we'll simplify x times the cube root of x cubed. According to our rule, this equals the cube root of x cubed times x cubed. When we combine, we get the cube root of x to the power of 8. We need to simplify the expression x, y squared times the seventh root of x cubed, y to the fourth. To simplify this expression, we'll use a very important rule for radicals. The rule states that a times the nth root of b equals the nth root of a to the n times b. For our first step, we'll rewrite the expression using this rule. We'll express xy squared times the seventh root of x cubed, y to the fourth, as the seventh root of x, y squared to the seventh power times x cubed, y to the fourth. For step 2, let's evaluate the power inside the radical. When we raise xy squared to the seventh power, we get x to the seventh, y to the 14th. For our next step, we'll combine like terms inside the radical. When we add the exponents for the x terms, we get x to the 10th. And when we add the exponents for the y terms, we get y to the 18th. Our final answer is the seventh root of x to the 10th, y to the 18th. Now, let's move on to our second example. We need to simplify negative a squared times the fourth root of 2a squared. We'll use the same radical rule as before. Remember, a times the nth root of b equals the nth root of a to the n times b. First, we need to be careful with the negative sign. We can rewrite this as negative times a squared times the fourth root of 2a squared. Next, we apply our radical rule to the expression inside the parentheses. We get a squared times the fourth root of 2a squared equals the fourth root of a squared to the fourth power times 2a squared. Let's evaluate the power inside the radical. A squared to the fourth power is a to the eighth. Next, let's combine like terms inside the radical. We have a to the eighth times a squared, which gives us a to the 10th. And we still have the factor of 2. We need to simplify the fourth root of 32x to the power of 9, y to the power of 5, z to the power of 12. To approach this type of problem, we'll use the property that the nth root of a product equals the product of the nth roots. We'll also use this important rule. The nth root of a raised to the power of n times b equals a times the nth root of b. For our first step, we want to rewrite this expression by factoring out perfect fourth powers. Let's first examine the coefficient 32. We can write 32 as 16 times 2. 16 is a perfect fourth power because it equals 2 to the fourth power. 4x to the power of 9. We can rewrite this as x to the power of 8 times x. Since x to the power of 8 equals x squared to the power of 4, it's a perfect fourth power. Similarly, for y to the fifth power, we can write this as y to the fourth power times y, where y to the fourth is a perfect fourth power. And z to the 12th power can be written as z cubed to the power of 4, which is a perfect fourth power. Now that we've identified our perfect fourth powers, let's rewrite the expression by separating the perfect powers from the remaining factors. We can write this as the fourth root of 16 times the fourth root of x squared to the fourth power times the fourth root of y to the fourth power times the fourth root of z cubed to the fourth power times the fourth root of 2xy. In the third step, we'll simplify the roots of perfect powers using the rule that the nth root of a to the nth power equals a. So the fourth root of 16 equals 2, the fourth root of x squared to the fourth power equals x squared, the fourth root of y to the fourth power equals y, and the fourth root of z cubed to the fourth power equals z cubed. This gives us 2x squared y z cubed times the fourth root of 2xy. Now, let's move to our second problem. We need to simplify the fifth root of x to the power of 12, y to the power of 4, z to the power of 24. We'll use the same approach as before, factor out perfect fifth powers, separate the terms, and simplify. For our first step with this problem, we want to factor out perfect fifth powers. For x to the power of 12, we can write this as x to the power of 10 times x squared. Since x to the power of 10 equals x squared to the fifth power, it's a perfect fifth power. For z to the power of 24, we can write this as z to the power of 20 times z to the power of 4. Since z to the power of 20 equals z to the power of 4 to the fifth power, it's a perfect fifth power. The y to the power of 4 doesn't contain a perfect fifth power, so we'll leave it as is. Combining these, we get the fifth root of x squared to the fifth power times z to the power of 4 to the fifth power times x squared y to the fourth power z to the fourth power. In the second step, we'll separate the expression by writing it as the product of the fifth roots of each term. This gives us the fifth root of x squared to the fifth power times the fifth root of z to the power of 4 to the fifth power times the fifth root of x squared y to the fourth power z to the fourth power. For the third step with this problem, we simplify the roots of perfect powers. The fifth root of x squared to the fifth power equals x squared. The fifth root of z to the power of 4 to the fifth power equals z to the power of 4. This gives us our final answer, x squared z to the power of 4 times the fifth root of x squared y to the fourth power z to the fourth power. Welcome to our mathematics video. Today, we'll be comparing different expressions to determine which one is larger. Let's look at our example. We need to determine which of these expressions is larger, 2 to the power of square root of 7, or 3 to the power of 13 over 8. Let's start solving this step by step. First, we'll work with the expression 3 times the square root of 7. We'll use the identity that a times the square root of b equals the square root of a squared times b. Next, we calculate 3 squared times 7. This gives us the square root of 63, which we can compare with 8. Since 3 square root of 7 is less than 8, we can write this as a direct comparison. So 3 square root of 7 is less than 8. Now, let's multiply both sides of our inequality by square root of 7. We'll use the multiplication property of inequalities, which states that if we multiply both sides of an inequality by a positive number, the inequality direction remains the same. Let's simplify the left side. When we multiply 3 square root of 7 by square root of 7, we get 3 times 7, which equals 21. To eliminate the radical on the right side, we'll square both sides of the inequality. When we square both sides of an inequality, we maintain the same direction if both sides are positive, which they are in our case. Let's calculate both sides. 21 squared equals 441. On the right side, 8 squared times 7 equals 448. Now, let's look at the other part of our problem. We know that square root of 7 is greater than 21 over 8. This means that 2 to the power of square root of 7 is greater than 2 to the power of 21 over 8. We can conclude that 2 to the power of square root of 7 is greater than 3 to the power of 13 over 8. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. Nenomatica, where mathematics meets YouTube excellence.